What's up, guys? Yeah, so my name's Arun. I'm on the Bee Harvest team. Thanks for coming out. We got a bit of a small, intimate group, so feel free to hop in some questions. We're going to do a few chats on some research and then go into a small panel. First, we have Florian from Cornell. We'll chat about Autobahn. Also, congrats to Florian for finishing his PhD yesterday. Yeah. Doctor. Now.
Yeah.
So, I'll let you take the stage.
Thank you so much, Arun. Everyone, it's great to be here. Today, I want to tell you a little bit about our work on Autobahn, which is a new Byzantine fault-tolerant consensus protocol that we recently published at SOSP. Now, I figure BFT doesn't need much motivation in this audience, so I'm going to keep it brief and jump straight in. Consensus is at the heart of our BFT stack, and what it promises to do is to implement the abstraction of a shared totally ordered ledger. Right? Every participant agrees on the same set of operations and does so in the same order. And this guarantee holds even under the presence of a subset of malicious participants. And this is clearly a nice abstraction to implement, or it's a nice abstraction to have, but implementing rather isn't easy at all. We have high demands of our BFT protocols. To be useful, they must offer high throughput, they must offer low latency, and well, to tolerate Byzantine failures, they must remain robust. And they must do all of this while dealing with the troubling reality of asynchronous networks, which famously, at least on paper, makes the whole ordeal impossible. Right? That will make for a pretty short talk, so what do we do? To deal with this, practical and actually deployed solutions look to partial synchrony. In this model, we use timeouts to simulate synchronous intervals and to try and detect faults. We're going to maintain safety at all times, but offer liveness only when synchrony eventually holds. In BFT theory, you might have heard this is often modeled as a global stabilization time, or GST, after which we magically expect that our timeouts hold. This model allows us to rigorously talk about what our protocol does, but there's a big gap between the bookish version and what we actually deploy in practice. In practice, this rosy reality of partial synchrony, of ever-holding synchrony, right, is of course a fiction. Right? Missed timeouts are common and contribute to all kinds of behaviors, ranging from DDoS, to network delays, to simple replica failures. Right? And the cause of such events doesn't really matter, so I'm going to bundle them on this umbrella term of a blip. What matters here is their effect. These temporary blips interrupt the progress of consensus and require us to take explicit action to recover. The point I want to make here is that these blips are not fringe cases. Instead, as the name partial synchrony should suggest, these blips are part of the common case. And this means that to claim good performance, partially synchronous protocols must perform well both in the absence of blips and when recovering from them. Existing protocols, however, do not gracefully handle this disconnect. And we demonstrated this with a simple experiment on a popular BFT protocol, in this case hot stuff, where we simulate a simple blip caused by single replica failure. Right, so in this graph, I'm showing you an experiment running with a fixed input rate, close to the peak throughput capacity, and on the graph, I'm showing the latency of a transaction relative to its start time. So, yes?
So would a blip be called, for example, like a leader failure?
That's a good example, right? Or anything that would cause that request to delay and a timeout to get triggered. So that would be the case for leader failure.
What are other common cases of blips? Because I would assume that if like a non-leader node fails,
yeah,
even for a bit, that it should not cause the entire network, because it was considered like this.
Right. So those could be simple events like network delays, right? Let's say you're running TCP and you have congestion overload. Right? That's something that can happen. You have heterogeneous participants. That's a common setup in blockchains, where one validator that gets elected a leader maybe isn't maintained by the most technically apt person. Right? That's not the Byzantine fault in the sense that it's malicious, but it's a real effect. And this is something we observed in many conversations, for example, with people at Miston. Could be a DDoS attack too, right? Whatever causes consensus to stall. And what I'm trying to motivate here is that this is something people don't think about enough. Anyways, in this graph, during the blip, you lose progress. That's the case for all partially synchronous protocols. And as a result, our incoming requests will form a backlog. Once the blip resolves and progress resumes, we'll have to work off this backlog. But we can only do so as quickly as our excess throughput capacity allows us to do. This can result in performance degradation that last well beyond the resolution of the initial blip. Because of that, I'm going to call this effect a hangover. Right? So this is a latency degradation or throughput, whatever it wants. Now, I think most people would agree that hangovers, just like in real life, are undesirable and best avoided. Right? Ideally, we tolerate a blip somewhat like this. During the blip, we lose progress. Right? We're not building asynchronous protocols. But once we recover, we'll instantly return latency to normal and recover all lost throughput. Right? So I'm going to call protocols that accomplish this seamless. Right? The seamless partially synchronous protocol should avoid hangovers, and perhaps obviously should do so without cheating and simply killing liveness altogether. Right? So in particular, we'll also want our partially synchronous protocols to not introduce more blips in the process. Okay? So this was some background on seamlessness, a robustness criteria I think we don't give enough credit to, but I was also mentioning throughput and latency as deliverables. So on this note, I want to now introduce Autobahn, which promises to satisfy all of the tough demands that we expect for BFT, as well as seamlessness. Autobahn promises high throughput, low end-to-end latency, and seamless recovery from blips. An orthogonal goal we pursued was to try to be as simple and modular as possible. So you can actually plug in your favorite BFT protocol into Autobahn's architecture to give it high throughput and to make it seamless. So let me talk a bit about how we do this. At high level, Autobahn consists of two key components. The first is a data layer that continues to transport batches of transactions at the pace of the network, regardless of interruptions to consensus. The second then is a consensus layer that consumes the data layer and reaches agreement on its outputs. Now, separating these two is actually a rather common idea and is not the main contribution we make. Instead, our challenge lies in finding the right balance on coordination. If we offer too few guarantees here, we'll end up with something that is no more seamless than existing protocols. If we offer too many instead, we'll end up with something that is neither simple nor performant. So with that said, let me start by telling you about the data layer. To support seamlessness, our data layer needs to have three key properties. Obviously, we need to make sure that that data can be reliably retrieved. And that requires us to confirm that at least one correct replica has stored the data. In order to avoid hangovers, we also want data dissemination to make as much progress as possible, ideally at the pace of the network. I'm going to call this property responsive dissemination. Finally, we want to be able to easily index all of our disseminated data so that consensus and recovery from blips is very efficient. So let's start at the top. The key unit in Autobahn's data layer is a car, which is just a fun way of describing the process of reaching availability of requests. A car starts with one proposer, like that's one replica that broadcasts a batch of transactions to everybody else in the system. Other replicas store this batch and acknowledge that they have stored the batch by returning a vote to the proposer. Finally, once the proposer receives enough votes to ensure that the batch is stored at least one correct replica, it can prove to other participants that this is really available. Okay? Nothing fancy going on here, very simple. I want to highlight that cars do not provide stronger guarantees like non-equivocation. So in particular, they don't stop a proposer from sending different data to different replicas. Right? And that's on purpose here because we're trying to be as efficient as possible. So with cars, we satisfy our key data availability property. Remember, this is important for seamlessness because it allows us to safely decouple data dissemination from consensus. Once we have cars, we chain them together in what we call a lane. Specifically, each new car issued by a proposer contains a hash reference to the preceding car. This implicitly creates a total order. Right? Most importantly, though, it allows us to uniquely identify the entire lane with just the last car, right? Which transitively proves the availability of all other cars. This is what gives us our instant referencing property. And we care about this because it enables consensus to commit long lanes with cost independent from its size. Finally, we take the concept of a single lane and expand it so that every replica governs its own lane. Each lane grows independently and without any timeouts. Having multiple lanes maximizes our throughput and guarantees that dissemination does not hinge on any single proposer, which could be Byzantine. Running them independently instead minimizes coordination and allows us to support flexible proposer speeds, which can be useful in settings with heterogeneous participants, which blockchains typically are. So with lanes, we guarantee our responsive dissemination property. Again, we care about this for seamlessness because it ensures that during blips, data dissemination can make as much progress as possible. So now that we've seen how our data layer works, we can now move on to consensus. But why do we even still need consensus? Well, if you recall, our data layer only offers weak guarantees. Right? If there is asynchrony or equivocation, our lane states can diverge between our replicas. So if you consider this example here, the replica on the left has only observed 2 blue cars, while the replica on the right has observed nothing. Right? Maybe nobody sent it, or maybe there was a networking delay. For the orange lane, the left replica has seen 1 car for position 4, while the replica on the right has seen a completely different one, maybe because the proposer equivocated. Right? This means that we need to actually reconcile these possibly divergent views, and we do that by reaching agreement on the lane state. This is where our instant referencing property comes back in handy. Remember, with instant referencing, we can uniquely identify an entire lane with just the latest car. So instead of reaching agreement on each car individually, we can simply propose a snapshot of our data layer by using the last car or the tip of each data lane. This simple cut transitively proves the availability of all cars in the lanes. And in particular, this means that the size of our consensus proposals is constant or independent from the length of our lanes. Right? This is vital for seamlessness because it allows us to commit a huge number of cars with just one tip cut, no matter how big of a blip we encounter. Okay? You'll notice I haven't actually mentioned how we reach agreement. And I'd love to tell you more about that, but I won't have time today, so learning about that is one of the pleasures you'll have reading the full paper. What I will do is briefly point out a couple of cool features. The first is a data synchronization subprotocol that takes advantage of our lane structure to fetch missing data, no matter how much, in just a single round trip. The next are a bunch of latency optimizations to minimize latency. These include ideas like a fast path or pipelining, pretty common things. The final cool feature I already kind of teased at is the fact that you don't actually have to use our specific agreement protocol. You could just plug in your favorite BFT protocol into this architecture and motorize it to achieve high throughput and seamlessness. Okay, before I wrap up, let me show you some experimental results. We evaluated Autobahn's performance against protocols in 2 categories. The first is hot stuff, which you've seen already. It has decent latency, but it has poor throughput, and as we showed, it is not seamless. We also evaluated a variant of hot stuff that tries to naively separate data dissemination and consensus, but this design is not very robust. I'm going to call these vanilla hot stuff and batched hot stuff respectively. The second class representative we pick is a protocol called Bullshark, which is a state-of-the-art protocol for achieving high throughput. Right, this comes from a newly popular class of DAG-based BFT protocols, which if you squint look almost seamless, but they aren't quite. The main problem is that these protocols are typically obscure and they have high latency. Okay, so let's show some numbers. Here, for the first experiment, I'm showing you throughput versus latency in ideal fault-free conditions. Autobahn, shown in green, matches throughput of Bullshark, which is the maximum achievable. Every replica is a proposer, while also having the lowest latency, actually comparable or even better to hot stuff at low load. Most importantly here, Autobahn has over 2 times better latency than Bullshark. Now, of course, my pitch for Autobahn was not just about performance during graceful intervals, but also recovery from blips. So since I already showed you how hot stuff deals with a replica failure, here I'm going to just revisit the example with Autobahn. I made this example a bit more difficult by increasing the timeout duration, but the takeaway remains the same. Hot stuff in blue, as you can see, suffers a significant hangover that is even longer than the initial blip duration. Right? So you can imagine if you have scenarios in which you frequently have blips, maybe there's delays in network, you never actually offer your advertised latency. Autobahn, in contrast, immediately recovers from blips and returns latency to baseline just as promised. So that already brings me to the end of this very short talk, so I want to briefly summarize. Autobahn shows how to build a BFT system that is not just efficient under partial synchrony in theory, but also in practice. It has better performance and robustness than contemporary protocols, and it's simple. You don't need to start from scratch, but you can actually build around the core that you already have. Autobahn is also already adopted in production at a couple projects. So if you're thinking what protocol to adopt in your own work or which to further improve on, I hope you'll look to Autobahn as well. Happy to take any questions now, but if you want to learn about it in more depth, feel free to check out the paper or shoot us an email at the following addresses. Thank you.
Are there any trade-offs?
No. So the only trade-off you could make is if you don't care about throughput, why run anything else than just raw PBFT? That's the minimal latency you can achieve. Maybe you supplement it with a fast path like a system like Ziziva. Still, we get very close to that by adding one more round trip for data dissemination. Right, so a core protocol is a very fast version of PBFT, combines some of those elements. If you want to take some optimistic risks, you don't even need to truly wait for availability, so you can kind of trade off. There's a lot of tunable parameters that you can exploit. The main selling point here is that you're truly getting the best across all three axes while being simple. And if you already have a protocol right now that you like, right, and has good latency, and you're just worried about making it more robust or giving it more throughput, add this architecture around it with data dissemination, and suddenly you have a protocol that gives you the maximum achievable throughput and is resilient to blips. Yeah, Patrick.
When you just talking fancy microphone here. When you've talked to teams that have adopted Autobahn in production, are there any interesting notes or learnings you've found around how they've actually? Because there are some open questions at the end of the paper around how to actually make it practical. So I'm curious if there's any interesting insights you've had from that.
Yeah. So the one I know about is we had talked to Improbable. They're building this chain called Somnia. They have combined this Autobahn design with compression, right? So they care about space efficiency a lot. So the batches they propose during the dissemination in our cars are actually compressed, right? But again, that's a practical implementation detail that's orthogonal to the design. Right? I described to you a logical architecture, and how you implement the different layers doesn't really matter. So for example, in our cars themselves, in our implementation, we don't actually send one batch, but we send a stream of mini batches over a window to amortize bandwidth. So those are implementation details that you can improve, but don't affect the core architecture. You can pipeline cars if you want to. Sure. That trades off, again, latency with garbage collection or worst case wastage, right? One thing I didn't mention is that this car design actually makes it so that Byzantine replicas can't even produce waste into the system unless they intend to commit it. Because all cars in a lane, besides maybe the latest one, are guaranteed to be committed. So you don't even have orphans in this design, which is the case in DAG-based protocols. You don't have coordination across the lanes, so it's slimmer and more performant and more robust.
Thank you.
Motorized. That means that this Autobahn can be combined with any other BFT protocol.
Right. So I was making the case that I wasn't actually talking about what is the agreement protocol that we use, right? We use some PBFT-based derivative that does pipelining and a bunch of other stuff, but that core can be any consensus protocol. The only thing that you need to change is the input to consensus is no longer batches of transactions, but instead it's just a snapshot of our lane. Right? So you can add this lane structure, pass that into consensus, reach agreement on the lane state, and then you add the synchronization protocol, which is almost nothing, right? It's what it says basically is, actually I have a bonus slide on this. So replicas might locally be missing data, right? Because they are possibly in divergent states. That was just weakly consistent. So when you reach agreement on a tip cut, you have to also request the missing data. Now what's unique in Autobahn, or what makes this so sleek for recovery, is the fact that we already know the entire structure, right? We have just a simple lane. It's not like in a DAG where you have recursive parents and you have to trace them back. I know exactly how many cars are in my position because I voted for the car in position 3. I know their hash chain, and because I voted in order, I know that at least one correct replica has all of the data in that chain. And that means no matter how long this chain is, you can simply ask one correct replica, or you broadcast it to everybody, and one correct replica will reply with all the data. Because you just say, give me everything between positions 1 and 3, and then you can verify that it's the data you actually wanted by checking the hash chain. And so this allows you synchronization in single round trip. So this plus the data lanes is what you'd want to strip around your modular consensus core to motorize it. Right? Ultimately, when you have the lanes, you still need to create your total order. You just interleave them in however way you want. Right? We do some round robin scheme here to try and make it fair, but it doesn't really matter. Right? Any deterministic scheme will do here.
Sweet. Thank you, Florian.
Thank you.